Okay, so let's get started, guys. Just a very quick recap of what we did previously. I introduced you to frame structures, how these structures were used to transfer the load from the ground, from any point of interest to the ground. That's what we discussed previously. I showed you how these structures can be intelligently tied up to give you a nice transfer of load. Now, in this class, okay, so before and after that, like I solved a very simple problem. It involved a knee frame, and we drew bending moment and shear force diagrams. Okay, so that's what we did previously. Now today's my aim is to delve a bit deeper into bending moment and shear force diagrams. Okay, just to give you a refresher, I think so you already are familiar with bending moment shear force diagrams. You have done it in the previous class, but I thought it would be a good idea just to give you a recap so that just to revive your understanding. And so bending moment shear force diagrams, that's what we are going to do. Different types of loads, how these loads are transferred, how the bending moments, shear force and the loads, how they are connected with each other, and based on those, that sort of mathematical connectivity, how do we get a pattern out of it? Okay, so this is the usual stuff. And okay, so before we get started, okay, I'll just introduce different types of loads. Let me just draw a sketch of a structure. Okay, so what we can see over here is a frame, a very simple frame. Okay, it has got frames in the front, in other words, it has got frames on all the four faces. Okay, so what are different types of loads to which this sort of structure can be subjected to? First of all, we have got a concentrated load. A concentrated load, what happens in case of concentrated load? We have, what we assume is like whatever load you have, we just squeeze it to a single point. Okay, so this can be an approximation. You can have a distributed load, but you can also assume that instead of that distribution, you just squeeze it and apply it at center of gravity. Okay, that is one assumption. Or you can have an actual load applied on that structure. So for example, if I have got a beam in the middle, like for example, if I have three beams, which I am showing double lines. Okay, so we have got three beams on this frame. Okay, so these are my three beams. So I can have another column resting on this beam. Okay, this can be a column of another structure, a supporting structure. Like imagine this is our classroom, and there is another classroom or there which has got a column in the middle. Okay, normally you wouldn't provide a column in the middle, but imagine you have another structure which has got a column in the middle. So this is a concentrated load, okay, which is being applied onto your structure. So the concentrated load, as I said, or you can have something hanging off this beam. This can be an industrial building, and you might have some machinery which is hanging off your beam. Okay, so that machinery, so this might be a machinery over here, and you might have hangers over here. Okay, and those are also type of concentrated loads onto your structures. Okay, so this is, I mean, like concentrated loads are very commonly encountered in structures, and you must know how to deal with them. And in structure analysis class, when I say how to deal with them, that is, as we discussed previously, you should be able to draw shear force bending moment diagram and find out the deflections of the structure. Now, in the case, so this is one type of loading. The other type of loading is a distributed loading. Okay, there are two types of distributed loading. Okay, one is sorry. One is uniformly distributed loading, and one is uniformly varying loading. Okay, or linearly varying loading. So in the case of uniformly distributed loading, what happens? We have, like in reality, most of the loads which are applied onto structures, they are concentrated loads. Okay, your desks, your chairs, you guys walking, they are all concentrated loads. Okay, but what happens is that these concentrated loads, if their number increase, okay, then we assume that instead of considering them as a concentrated load applied on this structure, okay, we assume that they are actually varying. Okay, so we assume that they are distributed. So your load on this structure, imagine you are sitting over here, okay, on this level, and your load on this structure, this is actually a concentrated load. But to make our life easier, okay, what we do is we assume that your load is spread out, and that, in other words, that load is uniformly distributed. So how do I work out your load? How do I work out my load? This is a class of 50 students, isn't it? So approximately there would be 50 to 60 people in this room. I would say, okay, there might be, in an emergency case, 100 students. Okay, so this room will be housing 100 students at a time. Then I'll find out the average weight of an individual. Okay, what is the average weight of an individual? It might be, say, 70 kg, 75 kg, that is the normal weight. So I take that, I multiply it with 100, I work out the overall load of 100 students. Then I divide it by the area of this load. So I would get a load per unit area. Is that right? Yes. So I got a load per unit area, which would be something like applied over here. Okay. So this is a load per unit area. So this is a patch load which I have applied on the whole structure. Okay. Now, if my intention is to find out the load of this beam, central beam, which I have drawn. Okay. This central beam. Imagine this is my central beam, okay, and I want to find out the load on this beam. What do you think? How should I do that? How should I find out the load? Obviously, your load on this beam will be uniformly distributed, but we have worked it out as an area load, isn't it? This is an area load. So how would I find out the distributed load on this beam? It's not a rocket science. What I would do is, I would assume that this half, I will find out what is called the tributary area. So this, I would assume that this load which is distributed on this whole roof, okay, on this whole floor for the upper story, but it's a roof for the people who are below. But on this whole area, this load, half of it is going to these beams, half of it is going to this beam, and this area which is taken by this one. So my area load, I'll multiply that with this length, and I will get a distributed load on this beam. Won't I? Do you agree?
Yes, sir.
Look, I have found the area load, isn't it? Now my load is, for example, some units per unit area. Isn't it? What would be the unit of my load, which I found now? The load of you people. Okay, that would be in, say, kip per feet square or kilonewton per meter square, something like that, isn't it? Of that order of magnitude. Now it has got area because it's per unit area. Now what I would do is I would multiply that with this length. Okay, so if I multiply that load, which for example say is 3 or 4 kilonewton per meter square. Imagine that's 4. It's not 4 normally, it's 1 to 2 kilonewton per meter square. But imagine it is 4 kilonewton per meter square. So I will multiply that with this length. So what would I get? Per unit length. Isn't it? And that per unit length will be the load which will be applied on this beam. Do you understand my point? Yes. So, and similarly for this beam, I'll take this tributary area because this much is going into this beam. And for this beam, I'll take this tributary area. Do you understand my point? So that's how I'll find out my distributed load on this structure. So that is the second type of load. The third type is linearly varying load. Now, in what situation can we have linearly varying load? Something which you have very commonly done. I think so you're still studying that. What is that? Linearly varying load. Where can you find linearly varying load? Can you quote? Can you give me any practical example? Sorry?
जवाब आंसर करो मॉडल बना लिया तुमसे जवाब आंसर नहीं दिया मॉडल
this is a dam which is subject to, your hydrostatic load is normally a uniformly varying load or linearly varying load, isn't it? Yeah, your hydrostatic load is normally linearly varying. You are doing fluid mechanics, aren't you? Yes, so the hydrostatic load is always considered as uniformly varying. Why? P is equal to gamma h. So gamma increases, your pressure increases as you go deeper into your into a body of water. Yes, please.
Sir, it is related to previous diagram. Is there a specific way to take tributary area?
Is there a specific way? Normally the tributary area, if you are doing a very quick approximate calculation, how do you do that? You just say that, for example, if we have this length, let me do it in blue. If we have this length, what we would do is, between these two I'll take a half, okay, and between these two, between this and this, okay, so I'll take a half of this length and half of this length, and this is actually the location of the beam, okay, I'll put B over here. So this is the location of the beam. On this side the half length, on other side the half length, yes, and then for this beam the tributary area is this half and that half, so that is actually the tributary area. For this beam, because there is nothing on this side, yeah, I'll just take the one side which is this half, okay, which is this half, and similarly for this side there is nothing on that side, okay, so it's only one-sided load which is running into these end beams, one-sided load. And however, on the middle beam you have got tributary area, tributary load coming from both sides. So that's how we normally do that, but you can do some FE analysis to find out what actually this length is if you want to dig deeper into it. Okay, so that's how normally we do it. But for normal calculation, I think so this assumption is fair enough and it gives you good results. Okay. Okay, so this is one scenario where you can have linearly varying load. The other scenario is like if I have a frame which looks like this, okay, and this is a frame which is fixed ended. Yeah, I'm just looking at a cross section. So I've got the same building, but it is having a frame like this. And imagine this is there is a snow load over here, okay? Snow load is placed over here. So what happens is that due to the wind, your snow gets accumulated over here, isn't it? You will have a snow accumulate. So this is also a linearly varying load then. For this one you apply a linearly varying. So that's also another common place where you can have a linearly varying load. This snow is normally drifted on the whole roof, and you can have a uniformly varying load in case of snow. The other place where you can have the linearly varying load is that wind load. Okay, in the city center where you have got lots of buildings, and how would you, what would be the profile of the wind load? The wind load profile is normally parabolic. And why is that? I'll tell you. So the wind load can also be considered as approximately linearly varying, okay, which is something like this. Although in most of the code of practices it is considered as a parabolic load, but this is also a first approximation for the wind load. So now what happens? Why do we have a zero load over here and reaching to the maximum? Okay, so as I said, in the case of city center, what happens is that you have got, when wind is blowing, yeah, in the city center, the wind doesn't reach the root or the base of the building. Yeah, the wind So the base of the building doesn't receive that much wind load. However, at the top receives the maximum load. Why? Because that's the maximum exposed area. The base which is above soil, obviously, okay, the base which is above soil, that one is not exposed to the wind load. Okay, only the top is normally exposed to the wind load. So therefore, the wind load is applied also in a varying fashion. You understand my point? So wind load is a function of exposure. Okay, like for example, if you for example, when we are swimming, what happens? Like when we jump into the pool, okay, the load, the hydrostatic load which is applied onto us, that is a function of our surface area, isn't it? Like whatever is exposed to the water, that hydrostatic load is applied on there. Do you understand my point? If I am just swimming in a shallow water, that's less area of mine will be exposed to the water, so I will be under less hydrostatic load. If I go into a deeper water, then all my body might be submerged in the water, and in other words, the whole body is exposed to the hydrostatic load. So same analogy can be applied to the wind load. Okay, imagine this wind load, and that is applied onto the structure. That's a function of the exposed area, the surface area. Okay, if there is more surface area, more wind load that would be attracted to it. Do you understand my point? Yes. Yeah. So these are the examples of some of the loads which can be applied onto a structure. Any question about these? Any question? Okay. Now, we have a quick refresher of a shape of shear force and bending moment diagrams. Okay, shape of the shear force and bending moment diagrams. So imagine, yes, any question?
No, sir.
Okay, so imagine we have got a beam. Okay, this beam might be this one or anyone else, which is subjected to some load which looks like that. Yes? Now, in this beam, we have got a simple beam subjected to some load. What we do is, what is our aim? Our aim is to find out the shape of the shear force and bending moment diagram. Okay? So what we do is, we take a very small differential element of this structure, a small differential element, we zoom in and we find out that this differential element imagine this is W of X, okay? So we have got a uniformly distributed load of W of X. We have taken this load facing up just for convenience. That's it, like this is just to satisfy or be in accordance with the axes which I've chosen. So my y, positive y, is facing up. So that's why I've taken my load also facing up. It doesn't matter. You can take it down also. Okay, but this is just a generic load which is applied on this structure. So a small element we extract from this one, and we have these loads applied. Okay, so this is a free body diagram. We would have a shear force, we would have some force in this direction, and we would have a moment in this direction. It's a beam, so a beam can take shear force and moment at every point. Yeah, in between the supports you can have shear force and moment applied at every point. Okay, so there are infinite locations where you have shear force and bending moments. So in order to counteract that, we would have an opposite shear force and we would have an opposite moment applied. Yes? Is that okay? Now what should we do? How should we proceed in this case? How should we proceed? What do we have? Okay, what are we trying to find out? We are trying to find out the relation between the applied load, the moment, and shear. That's what we are trying to find out. Why? Because as I told you, that there are infinite points in between the supports. Infinite points where you have shear force and bending moment applied. Okay? And if you are asked to draw a bending moment diagram or shear force diagram for the whole component, which means this one, that means you have to find out shear force and bending moments at infinite points, isn't it? So we want to avoid, it's not possible that we do. So we want to have an intuitive understanding of the trend which is normally followed, so that we follow that trend and we quickly draw our shear force and bending moment diagrams. Okay, that's what we are trying to do. That's why the relation between the applied load, moment and shear is important. Why? Because we don't want to find out shear force, bending moment at each and every point. Okay, there are infinite points in between. So we just want to find out the trend, and we follow that trend and we quickly draw our shear force bending moment diagram. That's what our aim is. Okay, so how do we go about it? How do we go about it?
The equation of motion.
So equation of motion, or the equations which are available to us, those are equilibrium equations. Okay, equilibrium is the step which equilibrium will give us some relation between the applied load, the shears and the moment. Okay, it's only equilibrium. So equilibrium, two equilibrium equations will be active over here. One is summation of forces in y must be equal to 0. Yes. So we can say that V in this direction plus W times dx. Yes.
Yes, sir.
Minus V plus dV. Okay, so what we are saying is, at certain point you have V and N applied on the structure. Okay, and as you take a differential step ahead, there is a differential increase in your shear and the moment. Yes, that's what we are saying. Okay, so that's why I have got dVs and dm written over here. Now, since this is a differential element, which means this is a very small element. Okay, so if I square it or take a cube of it, that will be even smaller. So in order to derive a system, I would assume that the higher orders, they are 0. They are so small that it's good enough to neglect them. Yeah, that's what I'm saying. Yes? So the squares would be all neglected. So
this WDX is the load?
this is the applied load. the same tributary load which is applied on this, but we are assuming that this is a funky shaped load. Okay?
Why have we taken its direction upwards?
So that's what I'm saying, that you can take it downward or you can take it upward, it doesn't matter. The reason I've taken it over here as upward, it is because that it is consistent with my axes, with the axes which I have chosen. Okay? So in other words, what can be a scenario? Look, over here we are developing intuitive understanding also. What can be a scenario which can give you upward? Can anyone think of a scenario which will give you an upward load? How can you have, like, this is the story above. And how can we have an upward load? G? Yes, or if there is a explosion. No, not earthquake. If there is an explosion. If there, for example, if I have a, God forbid, a cylinder, okay, a gas cylinder placed over here, and they explode, it actually apply load in all the direction. Okay, so your wall will be bursting out, your roof and floor will be bursting out. So that is an example. So if I have an explosion over here, so that can have a load which is applied in the upward direction. You see what I mean?
Yes.
Yeah? So that is, okay, so now, okay, so that would be equal to 0. So we can cancel out our V's and so that's what we get. That's what we get. Now what does this mean? What does this equation mean? What does this equation mean? Because look, we are trying to understand what these equations mean. It's not like we just point blankly, we take the equation. So what does this equation mean actually?
Shear force is equal to the area of load.
So this means that the change in shear is equal to the magnitude of the load. Isn't it? The change in shear is equal to the magnitude of the load, or in other words, whatever change you have in the shear in these two directions, that is equal to the magnitude, the load which is applied. Is that not the same?
Yes.
The change, whatever change in shear you have in between these 2 points, remembering that shear always is at the end. Okay, so you take any 2 point of your any 2 point of interest, and you find out your change in shear. That change in shear is equal to the applied load. That is the definition. That's what this equation is saying. The applied load is Wx dx. Yeah, is that right? Or in other words, if you take W, the applied load, is equal to differential, the first differential with respect to x of shear. That's what this is saying. So if your V, we can say V is equal to W dx, and if my W is constant, then my shear would be linear. Yeah, and so on and so forth. So that's what this is telling me. Yeah, so that's what my aim is, isn't it? To find out the relation between my applied loads, the shears, and the moments. Do you understand my point? Okay, now use the second equation, and that is you take the moment and
सही है। पर ये कैसे पता कि इसमें किस पॉइंट के बॉन्ड है? इसमें WHDX वाले क्वेश्चन क्लॉकवाइज रखे तो इसका मतलब है कि एंड इस पॉइंट पूरे के ऊपर मोमेंट डिटेक्ट कर रहे हैं किसी पॉइंट पे नहीं समीशन ऑफ मोमेंट पूरे इसके ये एक छोटा पॉइंट है जिसको अपन मानने चाहिए। क्या कह रहे हैं?
yes. Okay, I've just taken moment over here. So this moment is m plus v dx plus w into dx into the lever arm, which is half dx by 2, and
कुछ तो मोमेंट आम
minus m plus dm, which is over here. So these ones,
v into dx तो ये वाला
So,
तो ये डिस्टेंस d
we can kill this term. Why? Because it is dx square
मतलब इस एंड पे इस पॉइंट पे मैं dx पे
and
v into मोमेंट आम
what can we have? Okay, so we can have this one and this one getting cancelled.
Does that DM must have negative sign in the end. So the DM in there.
Yes, so this is negative. Minus m plus dm. Okay, so we have
एक ही सेकंड में लिस्ट कॉम्बिनेशन पूरे वर्ड्स के लिए टॉपिक में निकलेगा
okay. So now we have essentially a relation between moment and shear. Okay, so the moment is equal to the area of the shear force diagram, or it is equal to the magnitude of shear. Okay, so the moment is equal to the magnitude of the shear. That's what this relation is. So in other words, if my load is a constant, my shear would be linear and the moment would be parabolic. Yes, and so on and so forth. So let us write these equations over here. Should I rub it off? Okay.